Hello, welcome to my talk. Thank you so much for tuning in. It's a pleasure to be contributing to such a wonderful community. If you're new to the Elastic community, you've tuned into the right talk because in this talk, we're going to be discussing some fundamental concepts you need to know before getting started with Elasticsearch. So I hope you're ready to make a few notes. But before we get started, allow me to introduce myself. My name is Landy Simpson. I'm an intermediate software developer with 4 years of industry experience. Although 4 years doesn't seem like much, the fast-paced environments of small to medium startups can definitely help accelerate your growth. And although it can be daunting to learn something new in software development, there are so many helpful people that are writing, creating videos, and hosting conferences. We can all lift the weight of the learning curve by contributing back to our community. With that said, here is my shameless plug. I am also a writer. I love writing about software development topics. Not only does writing help me learn and grow as a software engineer, it helps others in the community that I love. I want to create a space where people of all levels feel comfortable learning software development topics without feeling intimidated. So please make sure to follow me on Instagram and Medium for great reading content. And if you ever have questions, please shoot me a message on LinkedIn. Okay, so one thing that's important to note is that regardless if you're a junior, senior, or intermediate software developer, learning new things takes time. When it comes to software development, you're never too wise to get stuck. Throughout my years, I used to think the more time you spent in industry, the less time you get stuck by trivial errors. But that's far from the truth. The truth is, no matter what stage you're in within your software development career, you'll always encounter a problem that will get you stuck. But that's the beauty of continuously learning. You're continuously challenging yourself. And to evolve, you must encounter problems that require critical thinking and problem solving. So what are some things you could do to get unstuck from an error? One thing you could do is assess the problem. We've all encountered a cryptic error message at least once in our careers. Sometimes it's cryptic because there's not enough details in the error message to make sense of it. Other times, there are gaps in our knowledge that prevent us from understanding the technicalities of the tool. When you can't make sense of an error message, you can't decrypt the message into layman's terms. Often, the most reliable source of information is the documentation of the resource you're using. However, if there are gaps in your knowledge that prevent you from understanding low-level technical jargon, then you might not be able to understand the documentation any better. In this talk, I want to walk you through an error I encountered when I first started using Elasticsearch. And I think it's so important to do these kind of walkthroughs because there's so much information we can learn by getting stuck on an error. So first, I'm going to briefly explain the problem. The cluster block exception. If you may have or may not have encountered this problem, and if you have, you may have seen some solutions online, but basically I'm going to take you through this problem and show you how I initially assessed it and then initially dealt with it, and then we're going to dive into what I had to do to actually solve the problem and understand the problem in its entirety, in which I'm going to introduce the concepts. When there are gaps in your knowledge, the best thing you can do is invest in learning about the thing you're using first, and then going back to figure out, how am I going to solve this thing? Often, we don't have the luxury to do so in industry, but it's worth during your spare time to watch a video or read something and really understand what you're working with. I'll take you through some essential concepts that you should know so you're properly configuring Elasticsearch and thereby reducing the risk of greater failure down the road. Lastly, I'll take you through the solution. Usually the solution is quite trivial, but that's because we can understand the problem in its entirety. Therefore, we can properly assess and come up with a solution. So I'll show you 2 solutions to the problem by the end. So let's dive into it. If you're unfamiliar with the cluster block exception, without giving away too much, it's an exception that locks your indices and prevents you from adding documents to your index. When I initially encountered the cluster block exception, I was running Elasticsearch in a Docker environment. I was performing a local experiment with a set of documents that took up about maybe 2 gigabytes of disk space. It wasn't much at all. When I first encountered the error, I had no idea what a cluster or node or flood stage disk watermark were. So already my initial assessment of the problem wasn't very useful because I couldn't understand 90% of the jargon that was presented. Nonetheless, I took stab at the documentation, and to nobody's surprise, I couldn't understand anything that the documentation was saying because I couldn't understand the jargon. But I tried a solution in which I deleted my indices and reran my migration script to add my data back to my Elasticsearch instance. And although this solution worked, it was a temporary fix. So at that point, I knew I need to take a step back and learn the architecture. And the first place I started was, what is Elasticsearch? Although this seems like a little too far back to start, it's a good segue into heavier concepts. And for those of you who are new to Elasticsearch, I think this is really important for you to know as well. Elasticsearch is a distributed, scalable analytical search engine, but it also supports aggregation of unstructured data. I know, it's a mouthful. Essentially, Elasticsearch is an infrastructure that allows us to optimize search functionalities, but it also allows us to understand data by aggregating it in an assortment of ways. The encapsulated architecture makes it easy to horizontally scale, which means we could throw more disk space or memory at it if needed with very little problems. It's built on top of Apache Lucene, which is an open source search engine library built in Java. I'll be referring to this library a few times throughout this talk, so keep it in mind. Elasticsearch's primary storage type is JSON. If you're not familiar with JSON, it stands for JavaScript Object Notation. This might seem familiar to you if you've used NoSQL databases like MongoDB. It's a structure that allows us to store data in a key value format similar to the visuals in the slides. JSON documents are flexible and allow for nested structures. They're easy to extend with additional data without needing to create or manage relations. Elasticsearch also exposes RESTful APIs, so we can interact and configure our data and instances. You might already be familiar with the document, search, and indices API, but in this talk, we will mainly focus on the cat, cluster, and node APIs, which might be a bit more unfamiliar. These APIs allow us to understand our Elasticsearch configuration, which is fundamental to diagnosing issues. I included the endpoints for all the APIs I utilized in this talk, so make sure to pay attention to the slides and take note. So let's briefly review some basic terminology before getting started with the other concepts. I know it's common to use the database analogy, and as tempting as it is to make those connections, they're not accurate connections, especially if you're using Elasticsearch version 6 or higher. So I'm going to refrain from using the database analogy, and I'll briefly explain why the analogy is inaccurate in a moment. So let's start with the basic document. A document is a JSON object. Some people call them key value pairs or key value stores or hash maps. An index is an optimized collection of JSON documents. In a moment, we'll talk about what makes indices optimized, but the overall high-level takeaway here is that it contains our data. Lastly, type, which is deprecated, is a structure that helps differentiate documents with the same index. And I think it's really important to address this particular term so we could clarify the relational database analogy. In the analogy, types were synonymous to relational database tables, but that relationship led to incorrect assumptions. The reason being is because types are not independent of each other like tables are. Their fields share the same Lucene field, so you cannot have fields that share the same name but have different data types. For instance, suppose we have an index called Instagram. We want to create two types of documents that represent the different types of uploads a user can do on Instagram. So we create a story type and a post type. In the story type, the field uploaded is a Boolean that represents if a story has been uploaded or not. However, in the post type, the field uploaded represents a timestamp for which a post was uploaded. Since I'm using the uploaded field in two different types within the same index, Elasticsearch will map these fields to the same internal Lucene field, in which there will be a conflict because these fields differ in data type. Whereas in relational database structures, you could have multiple tables with fields that share the same name, but each field is completely independent from each other across the tables. So overall, the analogy and the concept of types had to go. Whew, okay, so now we could talk about the juicy stuff, the core concepts. What makes Elasticsearch such an amazing tool is the ease of getting started. The default configuration is generous enough for us to get started without needing to know these concepts. But when solving the cluster block exception and other such problems, I had to return back to these concepts to get a better idea of how Elasticsearch distributes data. So let's start with clusters and nodes. Because Elasticsearch is a distributed system, it's made up of one or more nodes that act as a single application. Nodes are simply Elasticsearch instances which contain our indices, and a set of connected nodes is called a cluster. We could tell which node belongs to which cluster based on the cluster name. You can also think of nodes and clusters as a set of connected servers under one name. Increasing the number of nodes increases the cluster's capacity to handle and distribute data. All nodes within a cluster are knowledgeable about other nodes within the cluster. In fact, with the default configuration, all nodes can transport traffic. This means if a node is unable to fulfill a client request, it could transfer the request to a subsequent node. Nodes within a cluster can also perform HTTP requests. This allows us to perform CRUD operations on our indexes and manage our nodes and clusters. The Document Search and Indices API are examples of APIs supported by our index. Isn't that cool? We can also have multi-cluster configurations. This is also why cluster names are incredibly important. Nodes know the cluster they belong to by the cluster name. In this instance, we have two clusters called production and development, and each cluster has two nodes. This is one of the use cases for multi-cluster configurations, but please make note, you don't have to have a multi-cluster configuration to separate your environments. An important part of understanding any problem in Elasticsearch is understanding where and how to read the configuration of your Elasticsearch clusters and nodes. We can use the Nodes API to better understand the nodes within our cluster. The configuration tells us the number of nodes allocated to our cluster, the name of our cluster, and it details each node in the cluster based on the node ID. Also, notice it gives us the number of bytes our nodes is occupying in our file store. The total is the total size of all file stores. The free in bytes field is the total number of unallocated bytes in all file stores. Lastly, the available in bytes field is the disk space a node can utilize in the JVM. This is incredibly important to remember, so also keep this in mind. Now that you're familiar with nodes and a cluster, let's dive a little bit deeper and uncover how our data is actually being stored in an index. In the review, we discussed how an index is a collection of JSON documents. That was a very high-level interpretation of an index, so I'm going to be introducing a lower-level interpretation. The documents we add to our Elasticsearch index are actually distributed amongst shards. An index is simply a namespace for a grouping of one or more shards. In fact, under the hood into Apache Lucene, a shard is actually a self-contained Lucene index. This further explains why types were so problematic prior to version 6. So not only are we distributing data amongst nodes in a cluster, we're also further distributing data amongst shards in a node. This type of architecture is not only scalable, but it's fail-safe and it increases efficiency, and you'll see why. There are two types of shards, primary shards and replica shards. Primary shards hold our data that we index and can accept read and write requests, meaning we could fetch documents via an HTTP request to our nodes, which retrieves the documents from our shards, or we can add a document in which our primary shard can accept the change and then relay that change to a replica shard. Replica shards act as redundant data. They are our fail-safe mechanisms, but they can also accept read requests. So not only do replicas act as a fail-safe, it increases our read bandwidth, therefore increasing performance. This is one of the reasons Elasticsearch is optimized for speed. And because our nodes are knowledgeable, they can communicate to determine which shard on which node is available to answer a request. It helps distribute the traffic of client requests. So you may now be thinking, more replicas means better performance. And to that, I'll say both yes and no. Let's first go through a basic example of how replicas and primary shards are distributed amongst nodes in a cluster. In this diagram, we have two primary shards, PA and PB, indicated by the orange triangles. And we have two replica shards, RA and RB, indicated by the white triangles. Primary shards live on different nodes than their replicas. This guarantees that if a node crashes with a particular shard, then there exists a replica on another node that can evolve to a primary shard. This type of fail-safe distribution even holds when we add additional nodes to our cluster. The shards will be redistributed amongst the nodes, and no matter which node fails, we have a redundant backup available to fall back on. The one thing we cannot do in this system is add more primary shards. When creating an index, we could specify the number of primary and replica shards. However, once the index is created, you cannot modify the number of primary shards. You must re-index if you wish to add more. But you can add additional replica shards to an existing index, therefore increasing the read bandwidth. So let's go back to our initial diagram for a moment. Although Elasticsearch distributes shards in a fail-safe manner, can you foresee any potential problems with only having 2 nodes? Here's a hint. What happens if both these nodes fail? Technically, we can have this problem with any amount of nodes, but think of it this way. What happens if all the nodes containing primary shards crashes? In this design, our replicas become unavailable, so it's not as fail-safe as it should be. But with the power to create as many replicas and nodes as we need, we could create an architecture that ensures that even if multiple nodes holding our primary shards crash, we still have a node with replicas to fall back on. Conversely, if the node containing all of our replica shard fails, we still have other nodes containing replicas to fall back on in the case other nodes should subsequently fail. Although adding additional replicas is a great way to speed up read processes and fail-safe our data, there comes a trade-off. More shards increases the maintenance overhead. The time it takes to redistribute your shards will increase, and the number of shards to copy data will multiply. So it's important to remember, only use what you need. We could create an index and specify the number of shards used through a put request. In the slides, I've specified 3 primary shards and 2 replica shards. However, the number of replicas actually means the number of replicas per primary shard. So if we have 3 primary shards, Elasticsearch will allocate 2 replica shards per primary, which will total to 6 replicas in this example. We can verify the number of replica and primary shards through the cat API. The API will return the name of the index, a shard identifier, whether it's primary or replica, the status, the number of documents in the shard, the disk space used for the shard, the IP, which I haven't included here, and the node the shard is allocated to. In this example, we could see that there are 3 primary shards and 6 replica shards. This follows the configuration I specified in the previous slide. But there's something very interesting about this configuration. The status of all my replicas are unassigned. An unassigned status means our shard is homeless and doesn't have a node to reside. There could be a few reasons for this. In this example, I'm only working with 1 node. And as I've previously noted, replicas don't like to share the same nodes as their partnering primaries. However, another interesting reason this can happen is if we exceed the low disk watermark. Do you remember the problem I was trying to solve? It referred to a flood stage disk watermark being exceeded. I'll explain both low disk watermark and flood stage disk watermark in a moment. But first, let's do a quick review. Nodes are Elasticsearch instances which contain all of our indexes, and clusters are a set of nodes. Nodes are knowledgeable about other nodes within their cluster, and they can communicate with each other and transport requests between each other. We can also communicate with nodes via HTTP requests. This allows us to create, read, update, and delete data in the overall system. We also learned that an index isn't a single entity, but rather a collection of smaller entities called shards. Primary shards can accept read and write requests, but replicas can only accept read requests. We also know we can add additional replica shards to further fail-safe our system and increase read bandwidth. However, we cannot add additional primary shards to an existing index unless we re-index. Lastly, we learned shards can redistribute themselves amongst nodes whenever a node is added or removed from a cluster. However, shards can be unassigned to nodes in situations such as low disk watermark. Now, if we go back to the problem, we can decrypt the error a little easier. We know that there's a problem within our cluster, which causes the primary shards within the affected node to not accept write requests. However, being in read-only mode means both replica and primary shards respond to read requests. We also know that when our shards are in an unassigned state, one of the possible reasons is because of low disk watermark, which sounds related to flood stage disk watermark. This is a great point to be when solving an issue. We were able to logically assess the problem without making any assumptions about how the underlying system works. Now all we need to do to solve this problem is answer the following questions. What are these watermarks? Why are they being exceeded? And how do we come out of read-only mode? Now it's time to find a solution. At this point, you should be comfortable reading documentation, browsing Stack Overflow, and other such resources. With that said, I'm going to walk you through some Elasticsearch documentation. The solution in its entirety is quite trivial, so I'll briefly talk about my solution and the alternate solution. From the Elastic documentation, we can see that shards are allocated to nodes based on watermarks, specifically the low and high watermarks. A watermark is a threshold set on a cluster. These thresholds determine the behavior of shard allocation if we exceed a certain amount of disk space on our nodes. From this documentation, we can gather that once nodes exceed a low watermark, shards are no longer allocated to nodes as a preventative measure from hitting high watermarks. In fact, if we go back a couple of slides, you can see that although our primary shards don't have documents, they still require space on a node to exist. We can also theorize that although our replicas, we could also theorize that since our replicas contain a copy of our data, if there isn't enough space for them to exist, then we cannot trust there's enough space for them to reliably hold a copy of our data. So chances are, replicas of newly created indices will be in an unassigned state. We can verify this theory by further inspecting the documentation. According to the docs, replicas of newly created indices are mainly affected by exceeding the low disk watermark. The high disk watermark, on the other hand, affects allocation of all shards and attempts to relocate shards to other nodes that are below the watermark. However, the key word here is attempt. If there aren't any other nodes that are below the watermark, relocation can't happen successfully, which leads us to the last line of defense, the flood stage disk watermark. Once this threshold is exceeded, Elasticsearch attempts to protect the node from running out of disk space by enforcing a read-only measure until our disk utilization falls below the high disk watermark. In my case, when I encountered this issue, I had insufficient disk space on my machine to handle the data that I wanted to work with, even though that data was only 2 gigabytes. That's how much space I really had left on my computer. So, no amount of deleting and re-indexing would help in my situation. Using the Nodes API introduced earlier, I was able to verify this was the issue by inspecting the available free space. Therefore, my solution was to increase my disk space. You can do that by adding additional resources to your environment or removing unused applications and documents from your environment. If your solution is to free up disk space, you'll also need to take your index out of read-only mode, since Elasticsearch doesn't automatically do it for you. You can also find this in the documentation. Allocating more disk space is definitely a last resort in my opinion, especially for production environments. In production environments, you want to ensure that your watermark settings are configured appropriately. If your watermark settings seem a little too bootstrapped, then you can increase the thresholds. In this alternate solution, you can make a GET request to view your watermark settings and make a PUT request to the same endpoint to configure them. You have the option of configuring the persistent environment, the transient environment, or both. The transient environment means that the configuration will not persist post a full cluster restart, whereas persistent will. Now, as you see, the solution was incredibly trivial, but it was trivial because I could understand the resources that were available to help me. So before I wrap this up, I'd like to leave you with some final thoughts. There is no shame in getting stuck on an error. Regardless if that error is big or small, trivial or complex, there's so much you can learn if you take a step back to understand the error, and then by understanding the fundamental concepts, decrypting the error and reading the documentation becomes way easier. No problem is too embarrassing to talk about, so talk about them. I hope you learned something in my talk today. Thank you so much for tuning in. And if you have any questions, please feel free to reach out to me on any of the given platforms. Make sure you connect with me on LinkedIn. I love to see new faces. And I hope to see you again next year. So enjoy the rest of your conference and have a good day. Bye now.